Hello students, this is your instructor Dr. Ismail Bedran again from Qatar University, and we are going today to start the second law of thermodynamics in this course, Physical Chemistry for Life Sciences. And to start, so in this chapter we're going to cover these topics: entropy. We're going to talk about entropy in the second law. We'll also speak about the absolute entropies in the third law of thermodynamics. We'll also discuss entropy changes and focusing on the system. So in this chapter, sections 2.1 and 2.4 actually are omitted, so you don't have to worry about that. It's only these sections that we need to cover. So to start with, let us actually look at these data observations here. So in this picture here, you see an old rusted car, and this actually makes us think what causes this car to rust. So basically cars are made of iron, so you have iron in them, and with time and the iron will react with oxygen in the air, of course, and the existence of moisture to form iron oxide. So you can write the equation like iron, so you can write the equation iron solid plus O2 gas goes to iron oxide. It appears that this process happens by itself, what we call spontaneous in the language of physical chemistry. So this process is spontaneous in the forward direction. That means iron will react with oxygen to form iron oxide, but usually the reverse does not happen by itself. And so the question, why is that? Why things sometimes appear to happen in one direction, but they don't happen in the reverse direction? One other example is this bottle of perfume. Now, this bottle of perfume has perfume in it, so there is some gas trapped in this bottle, but once you open it, the gas will again spontaneously spit out of the bottle and fills out the container, the room or whatever this bottle in. But again, why the reverse does not happen? You don't see gas molecules just talking to each other and deciding to come back to the bottle. That's something we won't see every day. So why is that again? It's interesting. And examples goes on and on without stopping. This ball, when you bounce the ball, bounces one, twice, thrice, and so on until it rests in the ground. And this is a common physical behavior that we see every day. But you won't see a ball deciding to come back through the same path. So why? It's a philosophical question that many scientists and many people thought about it. If you have a solid surface and there's a kind of this eraser sitting on it, you give it a push, the eraser will move, of course, towards the force that is pushing until it stops. So this is also a physical behavior that we can study in physics, and we calculate the speed and the initial speed and whatever. But the reverse does not happen. There's never an eraser decide to move from rest, comes back by itself to the first place. These all observations, actually, they have forward and reverse processes. We can study the reverse and forward processes using physical laws, but there is no one single law in physics that dictates why the forward process is favored over the reverse process. It's only one law. It's only one law, which is the second law of thermodynamics, that states and dictates what happens and what does not happen. It's this second law that says to this process, it's giving a green line to this process. Okay? It's that law, the second law of thermodynamics, that says to this process to go on, gives it a green line, but says to the previous process don't. And as you might guessing here, the reason is actually goes all to something we call entropy. It appears that systems, they like to go from an order. Entropy means disorder, by the way. The word entropy, it is the same as disorder, what we call in Arabic fawda. It appears that systems, they like fawda. The whole world is actually in love of disorder. There's a lot of things. There's a lot of wars and volcanoes and chaos and viruses and COVID-19 all over the world. And it's easier, it appears to be easier to go from order to disorder. And you can think about this The best example of that is when you have a house or an organized room with all the, all the toys and everything on it, and sitting on tables and everything, and you bring 2 kids to this room. Okay, give them 5 minutes, they will make the place a mess, right? It's going to take you more efforts as a person to put everything back to place. Going from order to disorder is much easier than the reverse process. Think about building a building, for example. It takes so much effort and time and money to build a big building, a big tower. But it takes a few seconds, maybe a piece of a bomb to bring the whole thing down. So the process, in terms of physical chemistry, we say that the order here, we say that this place has something of low entropy. That means the order, the amount of entropy is low. But when you go to this order, there's a lot of entropy here. So if you call this S initial, and this is S final, then delta S for the forward process, it's delta S is equal to S final minus S initial. You get a positive number. This increase in entropy is actually the cause of these processes to move into a spontaneously. So if you think about all of these examples, the car rusts, when the perfume goes above the bottle, and all these examples, it's actually you're moving from a state of order into a state of disorder. In other terms, you're moving from low entropy to higher entropy, and this is why things happen the way we see it. Actually, this is why maybe we are seeing the world the way we see. This is why we maybe grow. This is my way why the universe starts from a small Big Bang into all of these planets and galaxies that we see. This is what the famous physicist Hawkins calls the arrows of time. The arrow of time, which is basically moving from past to future, it appears to be dictated by the second law of thermodynamics. The second law of thermodynamics is not just a law that you solve equations from. It's the law that dictates the whole universe. The second law of thermodynamics states that there's, of course, few definitions for it, but I like this definition, which is the entropy definition, which says the entropy of an isolated system increases in the course of a spontaneous change. In other words, delta S total should be bigger than 0. So what does that mean? That means if you have a system So what does that mean? That means if you have a system and it's isolated, and I think now you know what is an isolated system mean. Okay, it has these adiabatic walls, does not allow anything to escape, neither heat or matter. And there is, if you imagine a process happening, that an initial state goes to a final state, and this process is spontaneous. It's a spontaneous process. Then delta S for the whole system and the surrounding should be bigger than 0. If this is happening, then it's going to be a spontaneous process. That's what the second law is all about. Okay. So for spontaneous process, delta S total should be bigger than 0. That's the green light that dictates why things is happening, either for a chemical or a physical change or anything we see in the world. Here's a thought experiment I give to my students all the time that says prove that it's impossible to run an ocean liner, ocean liner means a ship, by taking in seawater at the bow of the ship, extracting internal energy from the water, dropping ice cubes off the ship. This question has two answers. One is the philosophical answers. You can just explain this based on the previous definition of entropy of the second law, but there is also mathematical proof for that. And you can think about this and maybe discuss it with your friends. Now we move on to the definition of entropy. So entropy itself, which is disorder, it's the thermodynamic definition of entropy actually concentrates on the chain of entropy ds that occurs as a result of a physical or chemical change. So the small letter D here represents a small change in entropy or anything. So when you say ds or dh or du, that means a small change. And we use the word infinitesimal here. Infinitesimal means small change. You can convert the D into delta, of course, as you learned in the previous chapter, if that function is a state function. Now, we define entropy to be actually that change in heat divided by the temperature in Kelvin. That brings us a units of entropy, which is equal to units of energy divided by units of temperature. So it's going to be usually joule per Kelvin or kilojoule per Kelvin. S is state function. We don't have to prove that. We can prove it in other. We can easily prove that S is a state function, and because of that fact, we can write ds is equal dq over delta t in the form of delta S is equal q over t. You notice here in this equation that delta S is equal q over t. So we use delta for S, but we never use delta for q. And you know why is that? Because q is not a state function. Entropy is a state function, but q is never a state function. The only non-state functions in this chapter are q and w. So keep this in mind. We don't usually say delta q. We just use q. And the subscript rev here means reversible. And we have two types of reversibility. We have mechanical and thermal reversibility. But first, reversibility refers to the ability of an infinitesimal change in a control variable to change the direction of process. Mechanical reversibility refers to the equality of pressure acting on either side of a movable wall. We're not very concerned about mechanical reversibility in this course, but we are more into thermal reversibility. The thermal one refers to the equality of temperature in either side of a thermally conducting wall. So, for example, when you boil water, let's say, you bring some water here, and you give it some heat, that water liquid will, of course, convert into gas. This process for water at 1 atmosphere, it happens at 100 degrees Celsius. So this is the evaporation process. So, of course, this will take time, but at each second and each fraction of a second, the temperature is constant. So the temperature of the gas in that case is equal to the temperature of the liquid, and this is what reversible means. The word reversible comes from the fact that when the gas goes back into liquid, this also happens at the same temperature. It's 100 degrees. So evaporation and condensation, they take place at the same temperature. So in this case, we say this is a reversible process. Okay? Reversible process means you can think about actually the word reversible as equal to slow. If the process happens slowly, then it will be reversible. Reversible means if you start from point A and you end at point B through a path, let's represent the path by this line. If you are able to go from B to A on the same path, then the process will be reversible. Okay? But if you go from A to B through this path, the blue one, and then when you go from B to A, maybe you have to go into another path, maybe this way, then this is not reversible. In this course, we're going to consider only reversible process, okay? And we're going to solve questions for reversible behavior. A non-reversible process maybe will happen when you, let's say you have a gas, okay? 1 liter of a gas, and then the 1 liter you suddenly expanded suddenly, like in a fraction of a second, to 5 liters of a gas. That process might not be very reversible because it happens suddenly, and when you reverse this, maybe it will take another path. That's why this is called irreversible. But nevertheless, again, as I said, we don't consider irreversible process. Let's only focus on reversible process in this case. Now, an easy application of this concept here is represented by this example. It says an organism inhabits a pond. Pond means lake, small lake. In the course of its life, the organism transfers 100 kilojoules of heat to the pond at 0 Celsius. Calculate the change in entropy of the water due to this transfer. Now, before anything else, we need to write what is given, and maybe I advise you all the time to write a schematic of the question. So in this example, it's example in slide 9. We have maybe an organism, probably it's a fish or a horsefish or whatever, sitting in a pond of water, okay? And that fish, it says, transfer 100 kilojoule of heat to the pond. So there is a heat going from the fish to the pond, 100 kilojoule, because of the fact that this heat is getting out of the fish. So it's minus Q for the fish, and it's plus Q for the water. That means this process is exothermic, because in this case we are considering the organism or the fish to be the system, and the water will be the surrounding. But in the question, he's asking about calculating delta S for the water. Because we are extracting heat from the fish to the water, the heat will be minus Q for the fish plus Q for the water. That means the temperature of the water will increase, and therefore the entropy of the water will increase. And we're going to prove this mathematically. So we have a Q here. It's equal to 100 kilojoule. And this is happening at temperature is equal to 0 Celsius. So you can say the solution for this question, you can say delta S is equal Q over T, Q reversible, of course, it's a reversible process, over T, which is equal to 100 kilojoule. If you put 0, of course, you will get 0 answer, and you get 0 in the exam. Because, so this is the incorrect solution. You get 0 here, because you have to convert everything to Kelvin in this chapter. The correct answer is delta S is equal Q over T, which is 100 kilojoule divided by 0 Celsius. That means 273 Kelvin. And if you do the math, you should be able to get a number that is 0.366 kilojoule, Kelvin minus 1, which is unit of entropy. Okay, entropy is measured by units of heat divided by by units of temperature, which is equal actually 366 joule per Kelvin. Usually the entropies we write them in joule, not kilojoule. This number is a positive number. So two things I always tell my students to do when they are considering physical chemistry problems. First is that you have to think about your answer. You have to think about the sign. You have to think about the value, if it's big or small, and the most important is the units. For me, this is a plus sign. That means the entropy is positive. That means delta S is positive, which makes sense because I'm transferring heat from the fish to the water. So entropy will increase in the surroundings. Well, that's good. 366, that's a reasonable number, and we'll make sure by the calculations that it's equal to that. And joule per Kelvin is units of entropy, so we're good. Okay? So always don't only do the math, but rather think about your answers, because this is not a mathematical class. This is not a mathematics class. This is a physical chemistry class. In physical chemistry class, you have to think about the physics, the meaning, the sense of this answer. One more question here is that suppose you put a cube of ice of mass 100 grams into a glass of water at just about 0 Celsius. So this is a similar question to that, where the ice melts. So when the ice melts, 33 kilojoule of energy is absorbed from the surroundings as heat. Okay, that makes sense. What is the change of entropy in the sample, which is the ice, and the surrounding, which is a glass of water? So we treat this question the same way we treat the one before. This is slide, I think it's slide 10. Yes, it is. And I like to draw a schematic of everything. So this is the cube of ice. Okay, my friends. And we put this in water. So this is your water. You can use color or whatever. So this is the ice and this is the water. And the ice melts. That means, I told you before that when you have solid, liquid, gas, this way is positive, this way is negative, right? So positive means this is endothermic. That means the solid, when it melts, it actually takes heat from the water because melting needs heat. It's endothermic. So you write minus Q here for the water, plus Q for the ice. So this process is endothermic. Endothermic means the ice is the system here. So it's endothermic for the ice, and it's exothermic for the water. But when we say endo, we means for the system. When I say this process is endothermic, I'm referring to the system. So how much is that Q? This Q is equal to 33 kilojoule. And this is happening at 0 Celsius. So same thing, we can say delta S for the system, which is the ice. It's equal Q over T, which is equal 33 kilojoule, divided by 273 Kelvin. And you will obtain an answer of plus, should be 100, around 120. You can double check that answer in your calculator, please. 20 kilojoule per mole, Kelvin minus 1. And for the surrounding, which is water, because this is a reversible process, we can say delta S surrounding is equal to minus 120 kilojoule Kelvin minus 1. In the question, there is 100 grams of Q of ice. So the one we are calculating here is the entropy, not the molar entropy. The molar entropy will be in terms of moles. In that case, if he asks you to, or if she asks you, whatever, to calculate the molar entropy, you use this. Delta S is equal to N delta S molar. Okay? So the one we are calculating, the one we calculate is the delta S. If you want ever to calculate delta S molar, then what you do is you say delta S molar is equal to delta S divided by N, and then you calculate the number of moles of the 100 grams, and then you divide this number 120 divided by whatever moles, you get an answer of kilojoule Kelvin minus 1 mole minus 1. Okay, the one we calculated is kilojoule per Kelvin. Or you can actually write in joule Kelvin minus 1 minus 1 minus 1, which is more reasonable. Anyway, the question does not specify if it's molar or not. In the exam, of course, I will be more specific and more accurate, and I will ask you, I will specify which one you want to calculate. So now, my friends, we move our discussion into something else, which is the entropy change accompanying a phase transition. And as we learned in the previous chapter, a phase transition involves the transformation of between phases, like solid to liquid or liquid to gas and whatever. Now, for that specific transition, we define something called a transition temperature. So, for example, for water, the melting point is 0 Celsius, but the boiling point is 100 Celsius, and this is called the transition temperature. But for other substances, of course, it's different. Like for ethanol, for example, it's around 80 Celsius for the boiling point. Now, that at that transition temperature, we say delta S transition is equal to delta H for that transition divided by the T of transition. An example of that of melting, so we say delta S melting or delta S fusion is equal delta H fusion divided by T fusion. Here's an example, a quick example here that says protein lysozyme, an enzyme that breaks down bacterial cells wall, unfolds at a transition temperature of 75.5 Celsius. The standard enthalpy of transition, as determined using DSC, is 500 kJ per mole. And this is one beautiful example of using a DSC, which will be discussed in the lab of this course. A DSC will allow you to calculate the heat of that transition. And he says calculate delta S transition. So basically what you do here is just divide that delta H divided by the temperature in Kelvin, you have to change that into Kelvin, and then you obtain the entropy of that change. Same thing we say for boiling, delta S boiling is equal delta H boiling divided by T, and so on. Now, vaporization is actually endothermic for all substances. Vaporization is going from liquid to gas, and as we said just previously, that this is an endothermic process. With one exception of little reference to biology, which is helium. Helium is different. You know, chemistry comes with exceptions sometimes. So therefore, all delta S vaporizations are positive because of the fact that delta S is equal to delta H over T. Since delta H is positive, T is always positive, then delta S is positive in that case. I just said something that is interesting. I said all temperatures are positive. Well, how does that happen when we know that the temperature can be negative, like we have negative 20, negative 30? But what I'm referring to is here is that when I say temperature in physical chemistry, I'm referring to the absolute temperature, which is in the Kelvin scale. We never use Celsius here. We always use temperature, the thermodynamic temperature, which is in Kelvin, to illustrate problems. So as you see here in this table, you are given substances with delta H vaporization, and they are all, of course, positive. And these are also for delta S. So having said that, what about the entropy that involves a heating? Because all the examples we talked about, melting, evaporation, condensation, this happening at a specific temperature, which is called the transition temperature. The temperature is constant in that case. But what if we are heating the phase itself? What if we are heating a liquid or cooling a liquid, or heating a gas or cooling a gas? In that case, we have a temperature change, right? In that case, you can define, it's not required to prove this equation, but you can define, you can find that actually delta S is equal to C, which is the heat capacity, times the ln of T final over T initial, where C is the heat capacity of the system. If you're working at a constant pressure, you can calculate, you can consider Cp, and if you are working at constant volume, you can actually use the Cv. So when you heat something, let's say water from 20 to 80 Celsius, T initial is 20, the T final is 80, so delta T will be a positive number. Ln positive number is always a positive number, and therefore, and C of course is always positive. In this case, you will have a delta S of positive value, which makes sense because when you heat something, the entropy will increase. For cooling, what happened, let's say when you cool a gas from, let's say, 300 Celsius to 100 Celsius, this could be possible. In this case, the T final is less than T initial, so after the ln you will have a small number, less than 1, a fraction. Ln a fraction is negative. In this case, you will have a negative value for delta S. And this makes sense again, because when you cool something, the entropy will decrease. That means the entropy will decrease. That means the system will become more ordered, right? More ordered. So you can use now this equation along with the other equations for the transition, which is this one, to solve a whole system like this. In this example, it says calculate delta S for the transformation H2O solid at 0 Celsius to H2O gas at 100 Celsius. For 1 mole of water, he's providing you with the CV of liquid water, Cp, and he's also giving you the melting point of water, which is 0, and the boiling point of water, which is 100. He also gave you the delta H of melting and delta H of vaporization. So the way you do this system, again, we use a schematic as usual to solve these questions, is that you want to think about it, you have H2O solid, which is ice at 0 Celsius, right? And you want to convert that into H2O gas at 100 Celsius. You cannot do this right away. This process involves many things. What you need to do first is you want to go from H2O solid to H2O liquid at the same temperature, which is 0. And then you want to heat the liquid into H2O gas, sorry, H2O liquid at 100, right? Celsius, and then you vaporize the liquid. So this is A, B, C process. So in this case, you have delta S here, called delta SA, and then delta SB, and then delta SC. And delta S total will be the total of these things. For delta SA, this is a melting, so you can use delta H fusion for the water divided by the temperature of the T melting of water, which is 0 Celsius. Of course, you have to change that into Kelvin. For delta SB, which is the heating, you can use CP ln T final over T initial, because you cannot use this formula here. If you want to use it, what temperature you're going to use? You're going to use 0 or 100 or the average? No, you have to use the formula that corresponds to the heating process. And then finally, delta SC, which is the last one, it's equal to delta H for the vaporization of the water. He's given to you divided by temperature of the water of the boiling point of water, which is 100 Celsius. You convert that to Kelvin. Once you do those all calculations, you add all the delta S's together, and you should be able to find an answer of 154.5 joule per Kelvin. So I want you please to try that and practice similar questions. These are very nice questions to play with at your pre.